morning and welcome back to another session of boundary layer theory. So, today we will talk about the boundary layer approximations. Now, before we start, I will just recall what we did last time. We used a momentum integral approach. And showed that rho times u infinity squared times b times what we call the momentum thickness, which is a function of x, was the drag, which is a function of x, and theta x was defined in this way: integral 0 to infinity u of x y by u infinity 1 minus u of x y by u infinity dy. So, this is for the flat plate boundary layer which we discussed last time, and we have another expression for the drag, which is the integral of the wall shear stress now. This tau wall is mu into del u del y at x comma 0. We will now look at a special case when mu is 0, that is the case of an inviscid fluid. Now, if you look at the expression for wall shear stress obtained from Stokes' law of viscosity, if you put mu equal to 0, then tau wall is 0. So, you have tau wall of any x is 0. So, if you put 0 over here and integrate this expression, you will get drag equal to 0. Now, we know from experimental observations that you do have a drag. So, this is referred to as the D'Alembert paradox. So, the conclusion is that we do not have any fluid with a viscosity which is exactly 0. However, we will see that sometimes in certain regions of the flow, the fluid flow behavior can be described by assuming that the viscosity is 0. That is done just to simplify the analysis. So, we will see, we will try to find out the conditions under which we can do that. Now, if you look at this expression for this theta, or which is the momentum thickness, if this is your plate and you upstream you have a uniform flow. If it is an inviscid fluid, it will slip along the plate, and if I take the look at the velocity profile at this section, it will be the same profile, uniform with the value of u infinity even at the wall. For a viscous fluid, the velocity at the wall will be 0. For an inviscid fluid, it can be non 0. Now, if u is u infinity everywhere, then this quantity u by u infinity will be 1, and here 1 minus 1, which is 0. That means theta of x is 0. So, this expression for the drag also will give you the same result. So, what I am trying to show you that this profile, velocity profile, which we have not yet proved that it will be like this, is consistent with the fact that the drag is 0, which was predicted from by integrating the wall shear stress. Now, we will try to find the scales for the boundary layer. So, we know that for we will look at the case of what I will call quote high speed flows. We will show that under certain conditions viscous effects are important only in a thin layer close to the wall, which is called the boundary layer. So, the solution which we have got using the approximate method yesterday showed you that you have a boundary layer. So, if I indicate the edge of the boundary layer by this dotted line, we showed that if you have an upstream flow with a uniform speed u infinity, a typical profile here, if we assume is of the same form here, and then if we have a gradient in this thin layer, so that it goes to 0, then if we put the origin here at the leading edge, x along the plate, y along the normal to the plate, then this edge of the boundary layer, which is y equal to delta x, this is like root of x. This is what we found yesterday. Now, today we will try to use order of magnitude analysis to find out what is the maximum value of delta, and under what condition you have a viscous effects confined only to this thin layer. So, I have said high speed flows will later on show that that corresponds to actually high Reynolds number flows. So, if you have a Reynolds number which we defined in this way, R e is equal to the upstream speed u infinity into some length scale L upon nu, and this L could be the length of the plate, or if it is a semi infinite plate which goes all the way to infinity, this L could be some distance from the leading edge to some point on the plate. So, if you are interested in knowing what is happening around this x equal to L, you will take L as your length scale. So, if this is much greater than 1, we will show that this if I say delta x is order of delta naught, we will show that delta naught by L is much less than 1 if R e is much greater than 1. So, this tells you how high is high. I started with the phrase which I put in quotes high speed flows. This tells you that u infinity is much greater than nu by L. So, this 2 equal to sign greater than sign means is much greater. Now, nu has the units of meter square per second. So, if we divide it by length which has units of meters, this quantity will be in meters per second. So, it has the units of velocity. So, now I have given you the answer which will show later on about what I mean by high speed flows. So, our goal now is to solve the Navier-Stokes equations. So, if you look at the x momentum equation, you are going to have rho times the acceleration, which I can write this u del del x plus v del del y, which is your
আমি কোথাও ওদিকে কোথাও পাইনি।
had a network problem. So, if you look at the x momentum equation, the left hand side is the mass times acceleration per unit volume in the x direction. So, the acceleration in the x direction is given by this operator v dot grad, which is u del del x plus v del del y acting on u. And the right hand side I can write as minus del p del x, where p is the piezometric pressure. So, this is the combined effect of the gravitational force and the net pressure force on the fluid particle per unit volume, plus the viscous force per unit volume, which is mu times del to u del x squared plus del to u del y square. Now, this is the full Navier-Stokes equations. For the case of fully developed flows in a duct, you have seen that this equation can be solved analytically. The reason being that in that case your v is 0 and u is a function of y only. So, del u del x is 0. So, this is the nonlinear term, because these are the linear terms in the equation. So, if the nonlinear term is 0, it is easy to get an analytical solution. Now, for the case of the boundary layer, that will not be the case. I will explain this by looking at a control volume. Suppose this is your plate and I will draw an enlarged view. Let us say this is the edge of the boundary layer. I will take a velocity profile at this section, which is going to have a shape like this, typical shape. Now, we will use a control volume with one face on the wall and a vertical face over here. We will take a rectangular control volume and apply conservation of mass to this, global conservation of mass. Now, the velocity profile here is going to be a uniform profile. So, if this is u infinity, this is also going to be u infinity. Now, suppose I call this O, A, B, C. You will see that the mass flow rate coming in to the control volume through this vertical face, which I am calling O C, will be the density into the velocity, which is uniform, into, if I say small h is the length of O C, it is going to be simply rho u infinity h. Now, the mass flow rate through A B will be, if rho is constant, rho into integral of u dy from 0 to h, and this is going to be less than m dot O C. The reason being, if I plot the velocity profile, u infinity u of x a comma y, let us say, versus y. So, what I am plotting is the velocity at this section. If this is my level u infinity and this is the origin 0 0, the velocity will start with the 0 value, increase and reach u infinity asymptotically. Now, this point I have called B. So, if I look at say y b, this integral, so this length is what I am calling small h, the height of this rectangle, this vertical length. So, I am integrating this u dy from 0 to h. So, that can be represented graphically by this particular area, and if you look at u infinity times h, that is going to be this area which I have shaded vertically. So, you can see that this is less than m dot O c. The reason being that if you look at how the velocity is varying from A to B, it is 0 at the wall and it increases, but it has not reached u infinity here. So, everywhere the velocity here is less than u infinity, whereas here everywhere the velocity is u infinity. So, that means more mass is entering this control volume through this phase than is leaving through the right phase. Now, this wall is impermeable. So, we know that m dot O A is 0. So, no flow is entering or leaving through this control volume. Now, if you have a case where more mass is entering per unit time through this phase than is leaving here, what will happen to the remainder? It has to go out through this from mass conservation. That means that m dot C B must be positive, but m dot C B will be this constant density into integral 0 to x a of v of x comma h dy. So, the v velocity or the vertical velocity is going to be a function of x and y. So, I put y equal to h because I want the velocity at the top and is varying with x. So, if we integrate this from 0 to a, so this is going to be positive. So, that can be positive only if the velocity is positive. So, that means that the v at x h will not be 0 everywhere. In the fully tapered duct flows, v of x y was 0 everywhere. Had v of x y been 0 everywhere, this mass flow rate would have been 0. Then you would have a contradiction that more mass will be entering the control volume than is leaving. So, that would be a violation of the conservation of mass, and since the density is constant, mass cannot accumulate inside the control volume. So, these are what are called non-parallel flows. So, once again I will draw this plate and indicate the edge of the boundary layer by dotted lines. Suppose I take a point inside the boundary layer and we look at the streamline through this point. Well, it is going to have a velocity component in the x direction, and we are saying that it will have a velocity component in the y direction. We will show that the vertical velocity is much smaller than the horizontal velocity under certain conditions. So, the resultant velocity here is going to be this. So, this is the v. So, the velocity vector is not parallel to the x direction, and if you draw the streamline through this, it is going to be tangent at this point. So, typical streamline will be of this form. The fluid is coming in the x direction. So, you have a streamline upstream which is parallel to the x axis. So, the fluid particle will move along the streamline because it is a steady flow. So, streamlines and path lines are identical. It will enter the boundary layer. Once it enters the boundary layer, it will acquire a velocity in the y direction and it will move in a path like this. Now, if I say this is x and this is y, and if I say the equation of this streamline is y equal to y of x, then dy dx for the streamline you know is V by u. So, we will show that if the Reynolds number is much greater than 1, then V is much less than u. That means that V by u is much less than 1, which means that dy dx, the streamline slope dy dx for a streamline is going to be much less than 1. So, the deviation from the parallelity is small. So, these are sometimes called nearly parallel flows. But that slight non-parallelity has a major effect in the solution. If you had a parallel flow, which was discussed yesterday, so had the streamlines been parallel, for incompressible flows which are steady, you can show that if I say this is the x direction and this is y direction, your V of x y will be 0 everywhere according to this coordinate system, and u will be a function of y only. So, these are what we call unidirectional flows. And for such a case, if you look at V dot grad f or V dot grad u, let us say for the x momentum equation, that is u del u del x plus V del u del y. In this case, you have V equal to 0. So, although del u del y is non-zero, it is multiplied by 0. So, the second term in the acceleration convective acceleration is 0, and here u is non-zero, but del u del x is 0. So, this is equal to 0. So, when in such a case the equation becomes linear and it is easy to obtain an analytical solution. For external flows, we have shown that if you go back to the previous slide, we have argued from mass conservation that V is non-zero. So, whenever V is non-zero, this nonlinear term will be non-zero, and that is what makes the solution of the Navier-Stokes equations for external flows more complicated than the solution of the Navier-Stokes equation for fully developed internal duct flows, where the streamlines are parallel, as I have shown over here. So, I have shown you the difference between the two cases, so that you can appreciate why this is more complicated. Now, our goal is to solve this equation. Of course, this equation cannot be solved by itself because you have more than one unknown. So, we have to look at the y momentum equation as well as the continuity equation. There are 3 unknowns u, v, p, and there are 3 equations. But that system which is nonlinear, and if you study the classification of partial differential equations, these are elliptic partial differential equations, these are not easy to solve. So, what we will try to do is we will try to make what are called a priori estimates and see whether certain terms in the equation can be neglected in comparison with other terms, and if so, we can obtain an approximate equation which is slightly different from the original equation, and if that approximate equation or set of approximate equations is easier to solve than the full equations, then it will help in the solution process. It may be an approximate solution, but approximate solutions are of two kinds. One is using numerical approximations and the other is using approximate analytical methods. Now, analytical methods are always useful. They give you an insight into the fluid flow, and you need analytical solutions to benchmark your numerical methods. So, that is what we are going to do now. We are going to see whether we can approximate these equations by an equation or set of equations which are easier to solve. Now, the problem is that before we have the solution, we do not know which term in the equation is important or not. U is unknown. So, del 2 u del x square is also unknown, del 2 u del y square is also unknown, all the terms in the equations are unknowns. So, we have some idea what is u or the order of magnitude of u from the upstream condition. We are saying the upstream flow is a uniform flow with a velocity u equal to u infinity. So, we can say that u is order of u infinity. So, let us see what is the order of the other quantities. So, if this is a plate of length L and if I put the origin at the leading edge and have a coordinate system which I have described before, then you see that the value of x is going from 0 to L along the plate. So, we are interested in finding the flow over the plate above or below, where in a region where x is going from 0 to L. So, clearly x is order of L. So, this symbol means order of magnitude. So, x is order of L and u is order of u infinity. Now, we are anticipating that for high speed flows the viscous effects are confined to a thin layer close to the wall, which we call the boundary layer, and we have seen the boundary layer thickness might vary with x. So, if this is y equal to delta x, we will say that delta x is order of some delta naught. So, this you can take to be the maximum value of delta x. So, we can imagine that we are taking something which is of the order of the delta at x equal to L. Now, without solving the equations, we want to estimate what is delta by L. We are anticipating that delta by L is much less than 1. So, our anticipation delta naught by L is much less than 1. Now, this will not be true for all cases. So, we will have to try and find the conditions under which this will be true. Now, yesterday I had just given you a brief introduction to what is called order of magnitude analysis. So, we will use this order of magnitude analysis to estimate the order of different terms in this particular equation, and then we will see whether one term can be neglected in comparison to other term or not. So, what is the order of a function? If I say f is a function of y, let us say, if I plot this f versus y, and let us say I am interested in going from 0 to some h, the function may have some kind of a form. We are interested only in, so if I say this is z and this is z equal to f y, this is the graph. We want to know what is the maximum value of this function. So, here you can see that the maximum value is occurring here in this example, and this value here is f max. I put the origin over here. So, this length is your maximum value. Now, if you want an average value, a convenient way to define an average value will be to integrate the function with respect to y over the range 0 to h, because we are interested in knowing what is the average value in the range when y goes from 0 to h. Now, the problem is f is varying with y, but if I integrate it with respect to y and plug in the limit 0 to h, it becomes a constant. So, if I divide this by h, you can take this as a measure of an average value. And this is exactly what we do if you want to find, say, the average velocity in a duct. So, this is the example I gave you yesterday. If you have flow between two parallel plates, and if it is fully developed, you know you have a parabolic profile. Now, if I say this distance is h, and if I put the origin at the bottom plate, then the volume flow rate you know is integral 0 to h u dy. This is the volume flow rate point unit depth in the z direction. Now, if you want the average value, it will be 1 upon the area, which is h times 1 into integral 0 to h u dy. So, compare this with this expression which I wrote over here. This is for any general function, you see it has the same form. Now, we will give a graphical interpretation to this. If when I integrate f from 0 to y, we get the area under this curve. Now, consider a rectangle which has the same area and base which is h. What would its height be? It will be perhaps this rectangle. So, this horizontally crossed rectangle has the same area as the area under this curve. So, this height is what we are calling f average. So, the average value will lie between the maximum and minimum values, as you can see it is lying somewhere here, and because it is a continuous function, you know that the average value here will be the value of the function at some point xi, where xi lies between 0 and h. This is assured by the mean value theorem. So, this will be your xi, whatever it is. Now, why are we doing all this? We will show that using this definition of the average, we can find out what is the average value of, say, derivatives with respect to y, and then we can get an idea of the order of magnitude of what is del u del y. All right. Now, we know from experimental observations and our approximate solution that you have a profile of this nature. So, if I say this is delta of x, now let us ask ourselves the question, what is the value of average value of del u del y? Of del u del y at, if I say this is some x equal to say x a, over the range y going from 0 to delta. We can take this average value to be an estimate of the order of magnitude of del u del y. Now, if you use the definition which I have just gave you, then del u del y average value we will write as 1 upon delta integral 0 to delta del u del y at x a y dy. Now, this is easily integrated, you will get 1 upon delta. So, integral of del u del y is u, and then you have to plug in the limits. So, you get u of x a comma delta minus u of x a comma 0. So, the first term here is the velocity at the edge of the boundary layer, which we know for this kind of a profile is u infinity, and the second term is the velocity at the wall, which for viscous flows is 0, that is your no slip boundary conditions. This boundary condition we will see cannot be enforced when we try to find a solution for the inviscid flow equations, that is your Euler's equations. So, this definition tells you that u average is del u del y average is u infinity by delta x. So, this is of the order of u infinity by delta naught, because we are saying delta x is of order of delta naught. So, we will say that del u del y is order of u infinity by delta naught. So, you see the numerator here is the order of u and the denominator here is the order of y inside the bounded layer. So, order of del u del y turns out to be order of u by order of y. So, in a similar process we will estimate the order of magnitude of the other terms in the Navier-Stokes equation. But before we do that, let me take an example. Suppose I take the profile which we assumed yesterday, that is u infinity into 2 y upon delta minus y by delta whole squared when y goes from 0 to delta, and u infinity for y greater than delta. Now, from here we showed yesterday that del u del y you can get by differentiating each of these functions which define the values of u in these two ranges. The first one will be u infinity into 2 by delta minus 2 y by delta squared. So, this is for y between 0 and delta, and this will be equal to 0 for y greater or equal to delta. So, you see the maximum value occurs at y equal to 0 and the minimum value occurs at y equal to delta, as you can see from here. If you take draw the tangent to the curve, del u del y here is tan of this particular angle from the vertical, and del u del y here is the tan of the angle from the vertical, which is 0. So, if you look at del u del y, here we are plotting y versus u. So, that is why it is the angle from the vertical. The maximum value for a profile of this nature is occurring at the wall. So, what is del u del y or del u del y max? The maximum value and the average value will have the same order of magnitude. So, this we know is del u del y at y equal to 0. So, if we put y equal to 0 here, this term goes to 0 and we get twice u infinity by delta of x. Now, compare this expression with this expression which we got. This was u infinity by delta x and this is twice. So, it goes like u infinity by delta naught, the order of magnitude is the same. So, I hope this example has convinced you that this definition of the average is useful in obtaining estimates of the order of magnitude of del u del y, provided we have some idea of what is u as y goes to infinity, and that we can get from the boundary conditions. Now, similarly we need to know what is the order of the second derivative. So, if I want average value of this, I will write it as 1 upon delta integral 0 to delta del 2 u del y square at x a y dy. So, this will give you 1 upon delta. Now, if I integrate del 2 del y square, I will get del u del y, and this is a definite integral. So, this will be x a comma delta minus del u del y x a comma 0. Now, this for this particular case is 0 and this is the maximum value. which is the del u del y at the wall. So, this order we know is u infinity by delta naught, and you have another 1 upon delta over here. So, this whole thing will be order of u infinity by delta naught square. So, you see that when you want to find del 2 u del y squared order of magnitude, the numerator here is the order of u and the denominator here is the order of y squared. So, what we will do is we will introduce non-dimensional quantities. Suppose I define a capital U which is u by u infinity, and we will define a capital Y which is y by delta naught, this constant value, which is a measure of the order of magnitude of the boundary layer thickness. So, we know that u is order u infinity. So, capital U will be an order 1 function, and inside the boundary layer we know that y is order delta naught. So, capital Y will be order of 1 inside the boundary layer. Now, you have to keep in mind the fact that if you go outside the boundary layer, this being an infinite domain, then y will be large. So, that case has to be treated separately. So, this problem has what are called multiple scales, and we have to do order of magnitude analysis separately in 2 different regions. So, right now we are doing it for the boundary layer region, that is the region close to the wall. Now, if you look at this quantity, say del u del y, I can write it as u upon delta naught into u infinity upon delta naught into del of capital U del capital Y. This will mean u is infinity into capital U and this small y, the dimensional quantity is delta naught into this capital Y. Now, we will argue that if u is order 1 and y is order 1, then del u del y will be order 1. So, when the coordinate and the function you are differentiating are both order 1, this will be order 1. So, this will be order of u infinity by delta naught. So, what this, and I compare this with the previous values which you have got, previous estimates, you have shown that u del u del y is u infinity by delta naught. So, what this means is that if you non dimensionalize the quantities using appropriate scales which make the variables order 1, then if you write the dimensional quantity, the dimensional gradient in this manner, the coefficient which is sitting in front over here of this will reflect the order of magnitude of this whole quantity. So, if you introduce the non dimensional variables which are order 1 variables into the equation, then at a glance you will be able to tell what are the order of magnitude of different terms in the equation. So, similarly, if I write down del 2 u del y square, so this is a dimensional quantity. Now, u is u infinity times capital U. So, you are going to have u infinity in del 2 capital U, and here you will get del capital Y squared, and here you will get delta naught squared. So, our argument is that since u is order 1 and capital Y is order 1, this derivative of capital U with respect to second derivative of capital U with respect to y del 2 u del y square will be order 1. So, this coefficient in front of it, if you have done it correctly, would reflect the order of magnitude of this whole term, and that is what you have over here, del 2 u del y square is u infinity upon delta naught square. So, with this idea we can now go to the equations and try to estimate the terms. So, first of all we look at the continuity equation. So, for incompressible 2D flows you are going to have del u del x plus del v del y equal to 0. So, this implies that del u del x is minus del v del y. Now, once again if you go back to the case of fully developed flows, you should see that each term in the equation is 0, that is v was identically 0 everywhere. So, del v del y was 0 and u was a function of y only. So, this was 0. Now, for the boundary layer flows, I have given you an argument using the control volume approach and considering that rectangular control volume right in the beginning, that none of these are going to be 0. But one thing is clear is that suppose this is 0.1, then this will be minus 0.1. If this is 0.2, this will be minus 0.2. In other words, we have the magnitude of del u del x, if I take the absolute value, will be the same as the magnitude of del v del y. So, this means that these two terms del u del x and del u del y in the equation must be of the same order of magnitude. So, this will help us in finding what is the magnitude of v. So, we come back to the case of the plate. We know that at the plate for a viscous flow u is 0, v is 0, and upstream u is u infinity, and this is what we have called x and this is y. So, we know what is the order of L, that is this quantity. Now, we are not able to get an order of magnitude of v from the upstream condition or from this boundary condition, because v is 0 here and v is 0 here, but we have seen that a non-zero v is induced inside the boundary layer because of viscous effects which push the streamline outwards. So, if you have a typical streamline which is coming like this, it will be deflected upwards. So, now if this is a streamline, you are going to have the velocity vector tangent to it, it will have a x component as well as a y component. So, one thing is clear is that u is order u infinity, this condition we are getting from the upstream flow, and x is order L, this is we are getting from the geometry of the plate. Now, what we do not know is the order of y inside the boundary layer, which we denoted by delta naught. So, similarly, let us say the v is order of some v naught. So, this v is induced by the viscous effect. So, we want to find what is v naught and what is delta naught. So, what we will do now is we will define non-dimensional variables capital X equal to x upon L. So, this is a order 1 variable for us. Similarly, we will define y equal to y by delta naught, which again is a order 1 variable, but of course, this is only inside the boundary layer. So, the boundary layer I will abbreviate as PL. Now, u will define capital U, the non-dimensional velocity, we will define as u by u infinity. So, this is also going to be order 1, and now we will define a capital V, non-dimensional V, which is v by this v naught. So, we will choose a v naught which makes this order 1. Now, you see that del u del x I can write as u infinity by L into del of capital U del of capital X. The reason being that from here the small u is capital U into u infinity. So, I am infinity being a constant, I can take it out of the derivative, and from here the small x is L times capital X. So, again L being a constant, I can take it out of here. So, you know that since u and x are order 1 variables, we are going to assume that del u del x is order 1. Now, this is sometimes violated in certain regions of the flow field which have to be treated separately, but for the time being we will assume that since u is order 1 and x capital U is order 1 and capital X is order 1, that this is order 1, not 1, but order of 1. So, order of del u del x is u infinity by L. Now, similarly, if you look at del of v del y, the dimensional quantity, this we can write as v naught by delta naught into del of capital V del of capital Y, because small v from this equation is v naught into capital V and small y from this equation is delta naught into capital Y. So, this quantity we say is order 1. So, del v del y is order v naught by delta naught. Now, this equation has told you that del u del x and del v del y magnitudes are the same. That means, the order of magnitude of this del u del y, sorry, del u del x and del v del y must be the same. So, u infinity by L must be same order as v naught by delta naught. So, we have an estimate here u infinity by L order of v naught by delta naught. So, without loss of generality I can say these are equal. So, from here we get a relation between v naught delta naught and u infinity and L. The relation is that v naught is delta naught by L into u infinity. So, let me write that expression again, v naught equal to delta naught by L u infinity. So, we have linked v naught to delta naught, of course, they are dimensionally different. So, we have the velocity unit here and this is non-dimensional. Now, we are anticipating that delta naught by L is much less than 1. So, v naught by u infinity, this is the ratio of the velocity scales in the y and x direction, is the ratio of the length scales in the x and y direction. This is what we have obtained. So, I will repeat, the left hand side here is the order of magnitude of the y velocity divided by order of magnitude of the x velocity, and the right hand side is the order of magnitude of y by the order of magnitude of x inside the boundary layer. So, if delta naught by L is much less than 1, then v naught by u infinity will also be much less than 1. So, that means we are saying that the v velocity, although it is non-zero, is much less than the u velocity. So, if we consider the streamline inside the boundary layer, streamline through a point inside the boundary layer, the tangent to this streamline is the velocity vector, which has a x component. It will have now, if this condition holds, then it will have a large x component and a small y component. So, we are going to have dy dx for a streamline, which by definition is v by u. This is going to be much less than 1 if delta naught by L is much less than 1. Now, let us go to the x momentum equation. We had rho times u del u del x plus v del u del y equal to minus del p del x plus mu del to u del y squared plus del to u del x squared. Now, we have not yet talked about the pressure scale. Now, from Bernoulli's equation you have seen that P and P has the units of rho v squared. So, for the time being we will define a non-dimensional pressure which we will call say P star, sorry it is not visible over here, P star to be P by rho u infinity squared. Now, this equation now I will write by introducing the non-dimensional variables. So, this u I am going to write as u infinity times capital U, this x I am going to write L times capital X, and this u infinity u I will write as u infinity times L. So, you will see that here you will have a term rho u infinity squared by L into u del u del x. Now, the advantage of writing in this form is we know that, or we are trying to argue that capital U del u capital X is order 1 if our scales are correct. So, the order of magnitude of the first term, the whole thing is reflected by this coefficient over here. Now, similarly the second term will be rho v naught into e infinity by delta naught into capital V del capital U del capital Y. So, this u infinity has come from this u, and this v naught has come from this v, and this delta naught has come from this y. Now, if you look at this term and this term, we can try and compare the order of magnitude of the two terms and see if one is small compared to the other, then you can neglect it. Now, we have a relation here that v naught is delta naught by L u infinity. So, here we have v naught by delta naught. So, v naught by delta naught is u naught u infinity upon L. So, this quantity is actually v rho u infinity by L into u infinity, this quantity. So, if you look at this and this, you see that these two are the same order of magnitude. So, we cannot say I will neglect one in comparison with the other, either both should be there in approximate equation or both should be ignored, but they are comparable, that is what we have got from this order of magnitude. Now, if I continue and write the right hand side, you are going to have minus rho u infinity squared by L into del of P star del capital X here. Now, we will come back to the pressure later on, but for the timing we see that if this scale is correct, then this term is the same order of magnitude as the other two terms on the left hand side of the equation. Now, we will come to the viscous term. The first one we will write as mu u infinity by delta naught squared into del to u del y squared, and our argument is this coefficient here reflects the order of magnitude of the entire term, because capital U and capital Y are non-dimensional functions which we are hoping are order 1 functions. Similarly, the next term is going to be mu u infinity by L squared into del to capital U del capital X squared. So, our argument is that this quantity is order 1, this quantity is order 1, this quantity is order of 1, as are these quantities, and the coefficients in front of the equations give you the order of magnitude. Now, let us compare these two terms. If, as we are trying to argue, that the boundary layer is thin, then delta naught by L is going to be much less than 1. So, this term is going to be much larger than this term, because if you compare these two, you have mu infinity in the numerator in both cases, but here in the denominator you have delta naught square, which is going to be a large quantity if delta naught is small, and this is L squared. So, this term can be neglected in comparison with this term if delta naught by L is much less than 1. So, if delta naught by L is much less than 1, then del 2 u del x squared magnitude will be much less than del 2 u del y square. So, physically it means that if the boundary layer is thin, the second derivative with respect to y is large, much larger than the second derivative with respect to x. So, physically this represents momentum diffusion in the y direction, and this represents momentum diffusion in the x direction. Now, so one particular simplification can be made if this is indeed true that delta naught by L is much less than 1, that you can neglect this term in the equation. Now, what is delta naught we do not know yet. Now, what we have found is there were 1, 2, 3, 4, 5 terms in the equation, 2 on the left hand side and 3 on the right hand side. So, you have a summation of 2 terms on the left hand side and summation of 3 terms on the right hand side. We have found that these 2 terms on the left hand side and the first term on the right hand side, they are the same order of magnitude, because we have this coefficient here the same, rho e infinity square by L, this is also rho e infinity square by L, and this was shown to be equal to rho infinity square by L. And we have found that this term could be neglected in comparison with this. Now, it is possible that you have one approximation where this 1, 2, 3 terms are the largest term in the equation and much larger than the other 2 terms. Okay. So, you can have a case that rho infinity squared by L is much larger than mu u infinity by delta naught squared. If this is true and delta naught by L is also much less than 1, then you have an approximate equation which is rho u del u del x plus v del u del y approximately equal to minus del p del x. Now, this equation, approximate equation, reminds you of Euler's equation for inviscid flows. It does not have the viscous terms, none of the viscous terms are there. If you solve this, you will find that the drag will be 0. So, that means this assumption cannot be true, that the this term is small compared to the other 3 terms. Now, you can also have a case where rho infinity squared by L is much less than mu u infinity by delta naught squared. So, if this is true and delta naught by L is also much less than 1, then what will happen is your approximate equation simply del 2 u del y squared approximately 0. So, what we are saying is that, see, we are trying to do a guesswork, we do not know what is the correct form of the approximate equation. So, we are trying out different cases. So, we found that if delta naught by L is much less than 1, this term can be neglected. Now, if this is a dominant term in the equation that is much larger than these 3, then you have an approximate balance equation which is simply del 2 u del y square equal to 0. But if we integrate this, you will have u of this form, del u del y will be some function of x and u will be a of x y plus b of x of this form. Now, the problem with this form is that it cannot describe the flow properly, because due to this term y, it will go to infinity outside the boundary layer when y is large, and you will not get a meaningful solution from this case. So, let us not go into all the details. So, by trying out various cases, you will see that you can get a meaningful solution which describes the physics properly and agrees with experimental results if and only if this term is of the same order as the other 3 terms in the equation. So, what we had done was case 1 was the first 3 terms in the equation much larger than this the first viscous term in the equation, and second case was the 3 terms in the equation are much less than this term. So, we will take the third case now. Rho u infinity squared by L is of the same order as mu u infinity upon delta naught squared. So, what we have done now is, if you go back to this equation, the rho u infinity square by L reflects the order of magnitude of the first term in the equation, the second term in the equation, and the third term in the equation, and mu u infinity by delta naught square reflects the order of magnitude of the fourth term in the equation, and the fifth one we are arguing is small compared to the fourth one, but that will be true only if delta naught by L is much less than 1. So, if I say that this is the case, then I have an estimate for delta naught. So, this tells you that delta 0 squared by L is order of mu u infinity by rho u infinity squared. So, what I have done is moved the delta naught square to the numerator and brought this rho infinity square to the denominator. Now, this I can write further as delta naught squared by L order, mu by rho I can write as nu, and you have an infinity u infinity in the denominator because you have a square here. Now, I can divide both sides by L and write this as delta 0 squared by L squared order of nu by u infinity L. Now, this you will recognize as 1 upon the Reynolds number based on the length scale L. So, if we take the square root of this, we find that delta naught by L is order of 1 by root of R d. Now, we can answer the question under what condition delta naught by L is much less than 1. That is something we have already assumed in the order of magnitude analysis when we neglected this term in the equation. So, delta naught by L is much less than 1 if R e is much greater than 1, because you have root of R e in the denominator over here. So, for high Reynolds number flows, for high R e flows, the x momentum equation may be approximated by rho u del u del x plus v del u del y equal to minus del p del x plus mu into del 2 u del y square. So, out of the 5 terms in the original equation, we have found that one can be neglected in comparison with the other 4, which have to be of the same order of magnitude. And this is we have also found the condition, that is when the Reynolds number is large. When the Reynolds number is not large, the boundary layer may be, you will not have a boundary layer, the viscous effect will be very, the region affected by the viscous forces will be large and you cannot approximate the equation by this. Now, we will show that this equation is much easier to solve than the full equations, but before we solve this equation we also have to do a similar analysis for the y momentum equation and see which terms in the y momentum equation can be neglected in comparison with other terms in the y momentum equation. I would like to emphasize that there is no approximation in the continuity equation, because the two terms in the continuity equation have to be of the same order of magnitude. So, you cannot neglect one in comparison with others for external non parallel flows. So, let us go to the y momentum equation now. So, now you have rho times the acceleration in the y direction. So, we can write it as v dot grad acting on v. So, v dot grad is this operator u del del x plus v del del y for 2D flows. So, this will now act on v, not u. So, this will be equal to minus del p del y. This p is your piezometric pressure. So, this term accounts for the effect of gravity as well as the net pressure force on a fluid particle, and then you are going to have the viscous term mu del to v del x squared plus del to v del y squared. So, this is a dimensional equation involving dimensional variables. Now, we will write the equation still in dimensional form, but by introducing non dimensional variables which are order 1. So, the first term I can write as rho u infinity v naught by L into u del v capital V del capital X. So, this u infinity comes from this u and this v naught is coming from this v and this L is coming from this x. So, this is capital X. Now, the second term will be rho v 0 squared by delta 0 squared. Then you are going to have v del y. Equal to this, you can write as minus rho u infinity squared by delta naught del of p star del capital Y. Then you are going to have mu into v naught by L squared del to capital V del capital X squared and mu v naught by delta naught squared del to capital V del capital Y squared. So, our contention is that if we have non dimensionalized variables by appropriate scales which make the functions and coordinates order 1, then this quantity will be order of 1, this will be order of 1. So, this expression here sitting in front of this whole term reflects the order of magnitude of rho u del v del x. Rho v naught square by delta naught square should reflect the order of rho v del v del y. Similarly, we will look at all those terms, we will take them to be order 1. Now, let us compare these two terms. We have one relation that, if you recall, V naught equal to delta naught by L u infinity. So, here you have a V naught square, which I can write as a V naught into V. So, if you look at rho V naught square by delta naught square, that is the order of magnitude of the second term in the equation, I can write it as rho V naught into V naught by delta naught square, and V naught by delta naught, you see from here, is u infinity by L. Now, I made a mistake here. This is not delta naught square, this is simply delta naught, because you have first derivative here. The delta naught squared is in the second term here. So, this is simply V naught square by delta naught. So, this we can write as rho V naught u infinity by L. So, you see that this quantity and this quantity, they are the same. So, that means again the first two terms on the left hand side are the same order of magnitude. Now, let us look at these two terms, the two viscous terms. Now, once again, if you compare the order of magnitude, you see that you have mu V naught in the numerator in both cases, and here you have L square in the denominator, and here you have delta naught square in the denominator. So, if the Reynolds number is much less than 1, then delta naught square is going to be much less than 1, or sorry, delta naught will be much less than L. So, this term can be neglected in comparison with this term. In other words, this is going to be the dominant term. Now, let us look at this term. Is order 1 by R e. So, this quantity I can write as mu into V naught by L squared into R e, because delta naught square by L square is 1 by R e. So, this is mu into V naught by L squared, and this one I can write as rho u infinity L by mu. Now, you see that the mu is cancelling out, and this L will cancel with one of this L squared. So, you get rho u infinity V naught by L, which is exactly what we have over here. So, that means if I underline the terms which are same order of magnitude, this term is same order of magnitude this term, and is of the same order of magnitude as this term, and this we can see is going to be much less than this, provided the Reynolds number is much less than or much greater than 1. Now, let us compare this term with this term. So, we will look at rho infinity square by delta naught divided by this quantity, rho infinity V naught by L. Now, rho infinity squared by delta naught divided by rho infinity V naught by L will be equal to rho infinity squared by delta naught into L by rho E infinity V naught. So, here you see that this rho is cancelling out, this U infinity will cancel with this squared, and you will get U infinity L by V naught delta naught. Now, V naught we have already expressed here in terms of U. So, this is U infinity L by this I can write as delta naught by L U infinity into delta naught. So, all I have done is I have substituted the expression for V naught in terms of U infinity over here. Now, you see that this U infinity cancels out and you get L squared by delta naught squared, or in other words I get 1 upon delta naught by L whole squared. Now, if the Reynolds number is much less than 1, then delta naught by L is, if the Reynolds number is much greater than 1, delta naught by L is going to be much less than 1. So, since you have the square of that, it is going to be even smaller and it is a reciprocal. So, this is going to be much greater than 1. Okay. So, the conclusion is that this term in the equation is the largest term. It is much larger than the term 1, term 2 and term 5. We have seen that term 1, term 2 and term 5 are same order of magnitude. This term 4 is much larger than those, and this term 4 anyway is much less than this. So, this equation then can be approximated by del p del y equal to 0. So, if R e is much greater than 1, then delta naught by L, which is order 1 by root of R e, is going to be much less than 1, and y momentum equation may be approximated by del p del y equal to 0, because other terms in the equation are much smaller than this term. So, I will make a summary of what are now referred to as Prandtl's boundary layer equations. The continuity equation is del u del x plus del v del y equal to 0, there is no approximation. X momentum equation will be rho, then you are going to have u del x plus v del y acting on u equal to minus del p del x plus mu into del 2 u del y square. The term mu del 2 u del y x square term is neglected, and the y momentum equation is, there is a drastic simplification, this equal to 0. So, this set is easier to solve than the full Navier-Stokes equation. It still has a nonlinear term in this equation. So, it is not as easy to solve as the Navier-Stokes equations for fully developed duct flows, where this term is 0. Now, here your unknowns are u, v and p. So, there are 3 unknowns and 3 equations. Now, the third equation tells you that p does not vary with x as y. So, p is a function of x. So, instead of writing the equation in this form, there is another alternative form which you will find. So, I will write that also over here, del u del x plus del v del y equal to 0 and rho times u del u del x plus v del u del y, and here I will write minus dp dx instead of del p del y. This could be a function of x in general or could be a constant. For the flat plate we can show that this is 0, but this equation holds for other types of boundary layer flows also, where the pressure gradient is non-zero. Now, if I write this as a total derivative dp dx and indicate it is a function of x only, then I do not have to write the second equation, it is implied. So, I can write just these two equations as an alternative to these three. Now, we need boundary conditions for solving these equations. So, if we look at the boundary conditions, one boundary condition at the plate at y equal to 0, u is 0. So, this is the no slip boundary condition, and you are also going to have v equal to 0, this for an impermeable plate. Now, I do not have time in this session to discuss the other boundary conditions, but I will simply write that as y becomes large. So, that I will denote this way, y by delta naught going to infinity, that is y becoming large compared to the order of magnitude of the boundary layer thickness, here u will approach u infinity. And you can give a condition at x equal to 0, u equal to u infinity. So, with this you can solve the boundary layer equations for the flat plate. Now, I will go back and refer to the equations over here. Now, you see that here we will show that this can be determined from the boundary conditions. So, you have two unknowns actually u and v, and you have a second derivative of u with respect to y. So, you need two boundary conditions in the y direction, and that is what you have. At y equal to 0 you have u is 0, and as y by delta naught goes to infinity, u goes to infinity, u infinity. Now, you also have a del u del x. So, you have one condition on u at x equal to 0, that is u equal to u infinity. Now, if you look at the v in these approximate equations, you do not have the del 2 v del y square term, there is only a first derivative of v with respect to y. So, you have this condition that at one condition at y equal to 0, v equal to 0. Now, you do not have del v del x anywhere in the system. So, you do not have to say what is del v del x. So, if you try to solve those equations and say that v goes to 0, that is not correct. Those equations cannot satisfy this condition, that v equal to 0. So, certain things have to be given up when you make an approximation. Now, if you solve the full Navier-Stokes equations, you may be able to impose this condition, but you have to have a domain where y is really large, very far away from the plate. Now, here although we are saying y by delta naught goes to infinity, we are actually very close to the plate, we are not. So, this y is large compared to the boundary layer thickness, but it is small compared to the length of the plate, because if you look at y by L, this is going to be y by delta naught into delta naught by L. Now, what we are saying is that this statement implies that y by delta naught is large, but it is multiplied by delta naught by L, and this thing may or may not be large. Okay. So, physically actually this match is what is called a Prandtl's matching condition, which we can discuss in the next session. Prandtl's matching principle. But for the flat plate it is not difficult to visualize that u will go to infinity. Now, what is the pressure gradient that we will find for the flat plate, and we will call it a day. So, this equation I will write in this fashion: dp dx equal to mu del 2 u del y squared. This is a function of x comma y, minus rho u of x comma y del u del x comma y, minus rho v x comma y del u del y x comma y. Now, you see that I have rewritten this equation as this term minus these two, and each of these terms can be functions of x and y, but this sum total of these three terms will be a function of x only. Now, I can put any value of y, I can put y equal to 0, I can put y equal to infinity. So, if I put y equal to infinity, it makes sense because we know what are the conditions at y equal to infinity. So, this I can write as mu del 2 u del y squared of x comma infinity minus rho u x comma infinity del u del x of x comma infinity minus rho v x comma infinity del u del y x comma infinity. Now, you know that u of x comma infinity is a constant which is u infinity for this case of the flat plate, and this was for all x. So, I can differentiate both sides and write del x of u of x comma infinity equal to del x of u infinity, which is 0. So, this term is 0 for the case of the flat plate. Now, this is an asymptotic boundary condition. So, we have seen yesterday that this implies that del u del y x comma infinity is 0. So, this term is 0. It also implies that del 2 u del y squared x comma infinity is 0. So, this term is 0. So, you can say that dp dx is 0 for the case of the flat plate. So, for the flat plate boundary layer, this is the plate, this is x, this is y, upstream flow is infinity. We will solve these equations: del u del x plus del v del y equal to 0, rho times u del u del x plus v del u del y equal to del 2 u del y square. The pressure gradient term is 0, and then we will solve it with boundary conditions at e equal to 0, y equal to 0, u equal to 0, v equal to 0, as y by delta naught goes to infinity, u approaches u infinity, and at x equal to 0, u equal to infinity. So, you can find an analytical solution to this using what is called a similarity transformation, and you can compare that with the integral equation solution which we obtained yesterday, and you will find that surprisingly the approximate method gives you pretty good accuracy compared to the exact solutions. So, we will have a tea break.